In the endless compasses of the universe, wherein systems whirl like brilliant coals in an enormous void, a significant puzzler has arisen that shakes the actual premise of our comprehension. In addition to being a puzzle, this enigma challenges the foundations of current cosmology. At the core of this secret lies a major inquiry. How quick is the universe really extending? We are on the verge of a scientific revolution as a result of our search for this answer, which may force us to reevaluate the very laws that govern the universe. Lambda cold dark matter, CDM, the standard cosmological model, has served as the foundation for our understanding of the universe's expansion for decades. This model sets that the universe's present status is the consequence of a mind-boggling collaboration between standard matter, dull matter, and a puzzling power called dim energy. As per Lambda CDM, the universe has been extending since its beginning in the enormous detonation, and this extension is represented by the Hubble consistent, a proportion of how quick worlds are subsiding from each other. Nonetheless, as space experts have refined their techniques and perceptions, a huge inconsistency has emerged. The Hubble tension is the name given to this difference. The Hubble strain alludes to the way that various strategies for estimating the Hubble steady yield clashing outcomes. Perceptions of the universe today recommend that the pace of extension is around 9% quicker than what is generally anticipated in light of information from the early universe. This irregularity has prompted a logical deadlock with suggestions that could overturn how we might interpret cosmology. The Hubble strain has its underlying foundations in two essential strategies for estimating the universe's extension. The first method involves looking at the cosmic microwave background, CMB, which is the universe's faint glow from the Big Bang. Cosmologists are able to infer the rate of expansion of the early universe by analyzing the minute variations in the temperature of the CMB. The European Space Organization's Planck satellite, which planned the CMB with phenomenal accuracy, gave a Hubble steady of around 67 kilometers each second for every megaparsec. The subsequent strategy centers around noticing far-off worlds and their redshifts, how much their light has been extended as the universe grows. This method depends on standard candles, for example, Cepheid variable stars and type Ia supernovae, whose inborn brilliance is known, permitting stargazers to measure their separation from Earth. When joined with redshift information, these perceptions yield a Hubble consistent that is essentially higher, around 73 kilometers each second for every megaparsec. In spite of this evident error being generally little, it has significant ramifications. On the off chance that the universe is for sure growing quicker than the standard model predicts, something urgent about how we might interpret the universe may miss. This acknowledgement has ignited extraordinary discussion and hypothesis in established researchers. Might there be new material science affecting everything that we presently can't seem to find? Is how we might interpret dull energy or dim matter deficient? Or is there an altogether obscure power impacting the universe's development? A lot is on the line, and the pressure between these estimations has not yet been settled. To handle this grandiose problem, space experts have gone to the most progressive hardware available to them, wanting to accommodate these clashing perceptions and open the insider facts of the universe's extension. The secret of the universe's development is profoundly entwined with the baffling power known as dim energy. This baffling energy is remembered to pervade all of room, driving the sped-up extension of the universe. Dull energy was first presented by Albert Einstein, who remembered a cosmological steady for his situations of general relativity to take into consideration a static universe. However, Einstein reportedly referred to the cosmological constant as his greatest blunder when it became apparent that the universe was expanding. However, this alleged goof ended up being prophetic. Astronomers discovered toward the end of the 20th century that gravitational attraction was not stifling the universe's expansion. Rather, it was accelerating. This speed increase couldn't be made sense of by customary or dim matter, prompting the restoration of the cosmological consistent as dim energy. Dark energy makes up about 70% of the universe's total energy, according to our current understanding. Despite being the strongest and most widely accepted explanation for the accelerated expansion, dark energy remains one of cosmology's greatest mysteries. Its inclination is as yet unclear, whether it is a steady property of room itself, a unique field, or something completely different. The disclosure that dull energy overwhelms the universe's energy financial plan has significant ramifications for a definitive destiny of the universe. On the off chance that dull energy keeps on driving the development at a speeding up rate, the universe could confront a major freeze, where systems float separated until they are as of now not noticeable to each other, and the universe turns into a chilly, dim, and forsaken place. Regardless of its focal job in cosmology, dim energy has up until this point escaped direct recognition. Its presence is derived from its gravitational impacts for the huge scope design of the universe. As the universe extends, the thickness of conventional and dull matter declines. However, the thickness of dim energy stays consistent, prompting what is going on where dim energy turns out to be progressively prevailing. The standard cosmological model's incorporation of dark energy has provided a framework for comprehending the universe's vast dynamics. Be that as it may, it has likewise brought up new issues. Could dark energy be a manifestation of a deeper, yet undiscovered, underlying theory? A few physicists have recommended that dull energy may be connected with quantum vacuum vacillations, while others propose it very well may be an indication of new material science past the standard model. One of modern cosmology's most pressing mysteries, dark energy's true nature could fundamentally alter our understanding of the universe if solved. In the mission to determine the Hubble pressure and reveal the mysteries of dull energy, cosmologists have gone to the most developed space observatory at any point built, the James Webb Space Telescope, JWST. Sent off in December 2021, JWST is ready to reform how we might interpret the universe with its uncommon awareness and accuracy. JWST's essential mirror, traversing 6.5 meters in breadth, is almost multiple times bigger than that of its ancestor, the Hubble Space Telescope. This enormous mirror permits JWST to assemble all the more light and notice fainter, more far-off objects than any time in recent memory. Moreover, JWST is advanced for infrared perceptions, empowering it to look through vast residue and study the earliest cosmic systems and stars that shaped in the universe. One of JWST's key missions is to quantify the extension pace of the universe with remarkable exactness by noticing far-off Cepheid factors and type Ia supernovae, each filling in as standard candles.